Good afternoon, my fellow ambassadors. So we continue solving story sheets. We have one coming all the way from CBU. It's on circular motion story sheet, it's chapter 7. Um, so we go straight right into it. The question says a wheel accelerates uniformly from rest to an angular speed of 25 rads per second in 10 seconds. A. Find the angular acceleration of the wheel. B. Find the tangential and radial acceleration of a point 10 centimeters from the wheel center. C. How many revolutions has the wheel turned during this time interval? D. Find the wheel's angular deceleration if it comes to a full stop after 5 revs, which is revolutions. So this problem is, I think, one of the easiest problems in circular motion. It's quite straightforward, so we go right into it to find the angular acceleration. So first of all, we get our data, and then our data, we have the speed in rads, speed 25 rads per second. The time we have is 10 seconds. And then this looks like a little data, but then we have more data. We have this is the final speed. We have the initial speed. I think you by now you know what the initial speed is, but if you want, you can pause this video and guess. The initial speed is 0 since it's starting from rest. That's easy. So now we can now go to our formulas using a formula that we can use to find the angular acceleration using the angular velocity and the time, which is the final velocity and the initial velocity. Velocity is just speed with direction. So now the one that we can use is this one. Imagine these were not in circular motion. We would have this acceleration is equal to velocity minus initial velocity, this is final velocity, over time. So now if we relate this to circular motion, it will be angular acceleration is equal to angular velocity final minus angular velocity initial over the time. So now we're going to put our values. We know what our final angular speed is. We have it there, 25 minus just 0, the initial, over the time t. So now this is now 2.5 because we have 25. We don't need the calculator for this one. 2.5 rads per second squared. These are the ones these are the units for angular acceleration. And then so this is the problem A. And then for the problem B, we are being told to find the tangential and the radial acceleration of a point 10 centimeters from the wheel center. So this is good data. We have more data. So we have part B. So now we have some data for part B. It's 10 centimeters. So this 10 centimeters is from the wheel's center. So it's the radius. So we have the radius being 10 centimeters. Now 10 centimeters can be converted to meters. You can use conversion factors, you can use anything, but at the end of the day, I arrive at 0.1 meters. For the sake of making this video short, I will not go through the calculations. So now for part B, so we have B, let's label it B1, B Roman numeral 1, and we are finding the tangential acceleration. So you know the tangential acceleration is given by the product of the angular acceleration and the distance from the wheel center, which is the radius. So the tangential acceleration is equal to the angular acceleration times the radius. This is actually a simple equation. So at, we found now the angular acceleration, remember. So we are going to say 2.5 by 0.1. So now the angular tangential acceleration will be equal to 0.1 when you multiply is, you don't need the calculator, but for the sake of sex, for the sake of the sex, we are going to find is 0.25, yeah. So 0.25 meters per second squared. Because the rads here cancel, we have rads there, and since, okay, these rads don't cancel, but then we have meters coming from the radius, so these are the meters here. They replace the radians. So then for Roman numeral 2, we are being told to find the radial acceleration, and then we know radial acceleration is actually just centripetal acceleration, and then AC is given by the angular speed squared times the radius. You can even say AR, it's all the same. Radial, centripetal, it's all the same. So now C is equal to the angular speed. The angular speed is this one, 25 rads per second. And then the radius is 0.1 meters. So this will now be equal to, we need a calculator for this one. Okay, but you can actually do it without a calculator, because 25 to the power 2 is 25 squared is 625, then times 0.1, that's 62.5. But then let's counter check with the calculator. To the power 2 times 0.1, yeah, so 62.5. 62.5. It's important to know the answer before you actually find it. You try to figure out the answer, because sometimes you may make wrong calculations, and then if you find that the answer is different, you try to change the calculators or try to change the answer that you found with your brain. So now we go to C. In part C, how many revolutions has the wheel turned during this time interval? So now this is the one that would be quite tricky. Relatively, it would be tricky compared to the others. And then to find the number of revolutions that this will tend, we must just first of all, we must find the distance that this wheel has been turning, the distance that it had taken. And then when you find the distance, we are going to divide it by one, by the distance of one revolution, knowing that one revolution is equal to 2 pi rads. I think that we know, or just p 60 degrees. But then since we're dealing with rads, so one revolution is equal to 2 pi rads. I think that is known. So now when you remember the equation in motion, in linear motion, plus v naught t, this is the one that's, this is the equation that we deal with when we are dealing with the other kind of motion. So this, I think this y naught is the initial distance, then this y naught is the initial position, this is the final position. So when you take it the other side, you have v naught is the initial velocity plus 1 over 2 acceleration time squared. So now this is just the distance, because when you subtract the final position minus the initial position, you get the distance, right? So this is just delta y is equal to v naught t plus 1 over 2 plus here 1 over 2 at squared. So now this is the equation. So when you relate this equation to the equation in circular motion, you're going to have something like theta. The distance will be theta, because this which example would I give? Allow me to, if I can use this space. No, let me just get a different plain paper. So if you have something, so it's here, so it's there, then it's moving. So when it moves from here to here, this distance will be our theta, right? This is how we're going to know the distance. If it moves there, it comes here, that would be our theta. And then if it did this, this would be 1 revolution, and theta would be equal to 2 pi. And then if it moves again, it will keep, the distance will keep on growing, the theta will keep on growing, and the theta can actually be more than 2 pi. For example, if it does 2 revolutions, then the theta will be 4 pi. So now that's that for this question. So that's how you must understand this theta. This theta is actually the distance that it revolves. So now this is equal to v naught t. Now we are going to move from the the one in linear motion to the one in circular motion. So this one would be w naught plus 1 over 2 angular acceleration t to the power 2. Since this is the angular distance, this one will be the angular speed initial, and this one will be the angular acceleration. So now we get right into it. So when finding our theta, this, we know what this is equal to. The initial speed is this one which we wrote in our data, so that's why data is important, right? So this thing is actually 0, and then we have 1 over 2 acceleration to the power, angular acceleration to the power 2 times time to the power 2. The angular acceleration, we have it, we found it here, 2.5, and then the time, we also have the time, 10 seconds. Then when you multiply this one, you can even actually do it like that, the calculator, because 10 power 2 is 100. 10 times 2.5, that's 250. You move the decimal, and then 250 divided by 2, that's 125. So I think the answer will be 125, but then let's counter check with the calculator. So we have we can say 1 over 2, that's 0.5 times 2.5 times 10 to the power 2. Yeah, 125 rads. Now we got to our, we're still on this question. So we found the theta. So we found the, allow me to refer back to this one. So we found this theta, how it revolved, eh? So we found that. So now imagine if theta was like from, let's say if theta was from there to there, we could have known what theta is. So let's say this is like the quarter of the entire circle. We could have known by dividing this distance by the 2 pi radians. So now here what we can do is, there are two methods actually. You can use the conversion factor, or you can just divide you can divide this one by 2 pi, because you know that 1 revolution is equal to 2 pi. So now the the revolution can be found by dividing by dividing by the same 2 pi. So now we can actually say 125 divided by 125 divided by 2 pi. So I find in 19.89. So you can also use the conversion factors. So where you can say 125 rads, because we know 1, let me put it here, since we know at 1 revolution is equal to 2 pi. So now we can multiply this one by 1 revolution over 2 pi. So then when we this is pi rads, so these rads and these rads, they cancel, then we remain with revolution. Then when divide this, we found our answer to be 125 divided by 2 shift pi. We found our theta to be now 19.89. I'm using 4 significant figures, but then you can use any kind of significant figures that you've been specified within the question. So that's rads, that's revolutions, since the rads, they cancel. So these are the revolutions that will be made. Then so that's it for this one. You can also use other methods. There's that other method whereby you equate, say, 1 revolution is equal to 2 pi, and then x revolutions is equal to 122 pi rads. 2 pi rads is equal to 125 rads. And then when you find x, you still come back to this one. So you can use any method that is easier for you. And then for the significant figures, usually what we do is we check out the ones in the question. So in the question there are 2. Yeah, in the question there are 2 significant figures. So you can actually write just 2 significant figures which will be this one will change that one, it will be 20 revolutions. So now we go to D. We go to D, which D we are being told to find the angular deceleration when it comes to a full stop after 5 revolutions. So we have at D we have data, which is after 5 revolutions. So that's our distance, that's our theta. So our distance is equal to 5 revolutions. Yeah, that's our distance. And then our what else? Yeah, that's what we've been given. The other data we'll be getting from this data. So now when you remember the equations in linear motion, we have final velocity squared is equal to velocity initial plus 2 acceleration times the distance. Why we've used this equation? We can use any kind of equation, and if you are stuck, just check out all the equations in linear motion, then check which one has the variables that you need. So this one, we need to find the acceleration, which is the deceleration, by the way. So we need to find the deceleration, it's here, and then we have the distance, we have the final velocity, and we also have the initial velocity. So check out what you have and then what you don't have. An equation only has is only allowed to have one unknown figure. So now this is the equation. So now when you relate it to equations in circular motion, you're going to have w squared being equal to w squared initial plus 2 alpha theta. So now this is the angular acceleration, angular displacement, angular velocity, and angular velocity also. This one is initial. So now here we make this one the subject of the formula because it's the one that we're looking for. So now we have w squared minus w to the power 2 minus w to the power 2 initial is equal to 2 alpha theta. When you divide both sides by 2 theta to get alpha 2 theta, we are going to have the acceleration being equal to w squared minus w I squared over 2 theta. Now here now we can just now plug in the values because we know we made it the subject of the formula now. So the final, you must be careful here, the final velocity, the final angular velocity is 0 in this case because it comes to a stop. This one was starting from rest, but now it goes to a stop. So now then the initial, the one that it had initially, we can put a squared here, it does nothing. The one that we had initially was 25 rads per second. This is the one that it had before it had gone to rest, rads per second squared over 2. And then our theta, for our theta, we are being told it's equal to 5 revolutions, but then we can't plug in 5 revolutions here. So we are going to convert 5 revolutions into rads, knowing that 1 revolution is equal to 2 pi. So we can say 5 revolutions is equal to, again you can just use the conversion factor over, we want the revolutions to cancel, so 1 revolution is equal to 2 pi. So we're going to cancel these revolutions, 2 pi rads, and then we are going to multiply 5 by shift 5 by 2 pi. So this is 31.4 rads. So you can actually use anything to convert, you still come back to 31.4 rads. And then when you multiply this one, 25 squared is 625, we already know that it's negative, over 2 by 31.4, we are going to have 62.8, and then we are going to divide 625 by 62.8, and our answer we are finding to be 9.95 rads per second squared. Now we have the negative there. So this is why it's deceleration, because we know deceleration is negative acceleration. So our answer is actually perfect, that we know. And then when you want to change to the significant figures which are in the question, you can just write it as 10 rads per second. So thank you very much. That's all from me, and bye bye. See you in the next video. Please remember to subscribe, share it with friends who may find it helpful. Bye bye. Together we can.